Okay, so I realize now that the audio to module 1 was pretty lousy, so hopefully I've got that corrected. It'll be better for this module. My apologies for the poor audio quality. But anyway, here we are in module 2, and I hope you noticed, you probably did, that there's not much reading here, right? Module 2 has, as a reading content, just like chapter 3, but only like the first, maybe not even half. There's only like 8 pages of reading. You think to yourselves, gosh, this is going to be great. This is going to be easy this week. Not so fast. The reason why I limited the amount of material to cover is because this is pretty tough sledding. It's like really, really important, and I want to make sure that we give you time to ingest all of this. Now, what are we talking about? The first part of this essentially talks about, well, why the sun moves through the sky the way it does during the course of a year. But before we even get that far, I want to talk about how to map out the sky. We talked a little bit about this last week, or in the first module, about the celestial sphere. And I introduced you to the celestial sphere. Hello, I'm the celestial sphere. So when you're out tonight, take a look at the sky and say to yourself, okay, gosh, isn't that a pretty star out there? How can I tell somebody else about that star? Well, gosh, how do I tell somebody else like where I'm located here on Earth? I need coordinates, right? Like if I wanted to tell you to go to Tupelo, Mississippi, we didn't have any maps or anything, how would I tell you? I could tell you a couple of coordinates, right? Latitude and longitude. And if with those two pieces of information, you could find Tupelo, Mississippi. Now, what about that star? How would you tell somebody about that? There's actually two systems for doing it. One way would be to say, well, first of all, everyone has a horizon, right? So how high above your horizon is that star located? And you can measure it off in degrees. But the next question is, well, gosh, which horizon am I talking about? Because if I say it's 30 degrees above the horizon, that could mean here, it could mean here, it could mean here, it could mean whoop, here. So that's not good enough. I need to know which horizon I'm talking about. And that gets into a term called azimuth, which we're going to describe. But even that, once I know the altitude and the azimuth of that star, even that is not good enough because, well, gosh, just what happened? Remember, the Earth is rotating eastward. So just in the time that I've been talking about altitude and azimuth to you, what has happened to my star? It has, whoop, moved on me. And therefore it's changed its numbers. Now it's no longer at the same altitude or the same azimuth. It's changed its position. That's tough because it's going to constantly be changing because the Earth keeps on spinning. So I can create a coordinate system like this, but it's not going to be very useful because it's always going to be changing. I need a more static way of determining the locations of the stars in the celestial sphere, and so I use a system called declination and right ascension, which we'll be talking about here in a few slides. And once you understand that on the celestial sphere, it can then be easily used and translated to one of these devices. This is something I would do with my traditional class. I don't do a whole lot with the online classes because you can't put your hands on these things. But this is what's called a planisphere. It's essentially a celestial sphere gone from 3D down to 2D. But it uses these coordinates, declination and right ascension, in order to pinpoint the location of any star in the celestial sphere. So more details coming up about that in the next several slides, and that's where we really have to start. We need to first of all figure out, how do we map out the sky? How do we give it coordinates so that I can pinpoint any star I want at any time? Okay, so latitude and longitude. This is pretty straightforward. I hope that most of you are familiar with the latitude and longitude system. This is, again, how to figure out where you're located anywhere on the Earth. And what you do is you use the equator as your first kind of place to start. The equator has a latitude of 0 degrees. And then you just decide, okay, well, how far north or south are you of the equator? The North Pole, for example, has a latitude of 90 degrees north. It's 90 degrees north of the equator. And in a similar way, the South Pole has a latitude that is 90 degrees south of the celestial of the equator. Now, of course, knowing just latitude is not good enough, so you need to know another value, which is longitude. Longitude is how far east or west you are located compared to this line, and again, this is rather arbitrary, but it's the line that goes from the North Pole through Greenwich, England, and to the South Pole. That's what's called the prime meridian. And then once you've established the prime meridian is 0 degrees longitude, then you decide, okay, how far east or west are you of the prime meridian? And so your longitude value will increase and increase and increase until you get to 180 degrees. Halfway around the globe, you hit what's called the international date line. And so your maximum value for longitude can be 180, either west of the prime meridian or east of the prime meridian. So if I'd gone the other way, I'd still wind up running into the international date line. I'd just be approaching it from the other direction. I'd be coming from the east. So knowing all this, to find the coordinates of any spot on Earth, so for example, I can choose, I'm always a homeboy. I choose Mississippi, right? Tupelo, Mississippi, approximately 34 degrees north and about 88 degrees west. So those are the latitude and longitude values. And again, if you want to, this thing will actually show some cities, and you can actually open it up on Google Maps, etc., etc. But this is the basic idea between latitude and longitude. Okay, so I gave the example earlier about how would you pinpoint the location of a star in the sky. We've already talked about how to pinpoint the location of someone on the Earth. You need 2 coordinates. Same thing with a star in the sky. You see a star that looks interesting. Let me move my star over here. And you say, well, gosh, I'd like to be able to share that with somebody else. I'd like to tell them where that star is. And I'm actually going to take it from the point of view of our little person here. So, gosh, how would we talk about that particular star? Well, you could approach it by looking at how high is that star above the horizon. Notice if you were looking straight overhead, if you look straight overhead at a star, well, notice the angle that that star makes with respect to the horizon. It's 90 degrees between the horizon, any horizon, and the star. So notice the highest value you can get for that value, for that coordinate is 90 degrees. We call this dimension, we call this altitude. Altitude, how high above your horizon is the star? So in this case, where my star is, it's 26.4 degrees above the horizon. But notice any of the star, any location along this circle would have a altitude of 26.4 degrees above the horizon. So saying altitude is not good enough to pinpoint that particular star. I need to know which horizon. And here's where you have to introduce another concept called azimuth. And I'm now looking above my little dude there. And I don't think I can write on this, but what you need to understand for azimuth is that due north is 0 degrees azimuth. Due east is 90 degrees azimuth. Because can you see there's a right angle there? When you go from due north to due east, isn't that 90 degrees? So sure enough, north is 0 degrees azimuth. East is 90 degrees azimuth. South is 180. West is 270. Notice I've just gone up in increments of 90 each time. So now if I want to pinpoint which horizon I'm talking about, I can see that my particular star here is located somewhere between south and west. It's somewhere between 180 and 270, isn't it? Well, sure enough, when I go back down here and take a look, yes, it's 235. So that spells out to anybody I'm talking about that it's because my azimuth value is 235. It's somewhere between 180 and 270. I have to look toward the southwest in order to see this particular star. So my altitude is 26.4 degrees above the horizon. Which horizon? My horizon is 235 degrees. That tells somebody that it's not due north, it's not due east, it's not even due south or due west, it's somewhere between south and west. Okay, so that's how the altitude and azimuth system works. The problem is that is attached just to a particular observer. If I notice that star from Tupelo, Mississippi, and I call a friend in Sacramento, California, they're going to have a different horizon, and therefore they're not going to get this. If I give that person those values, they're not going to find the same star that I'm talking about. So it is unique to an individual, and it also changes because if I wait, and 15 minutes later, that star will have moved because the Earth is rotating eastward, the stars are moving in my sky, I would have entirely new values for the altitude and azimuth of that star. So this is a useful system, but it has limited usefulness.
Okay, so here we see what's called the celestial sphere. Again, inside you should notice there's the Earth, there's the globe we're all familiar with, and it's got, of course, its lines of latitude, which we've already talked about. There's the equator, latitude 0, and then these lines, or these circles, are lines of latitude, essentially measuring how far north or south you are of the Earth's equator. And this is measured in degrees. And so the farther north you go, eventually you start out at 0 degrees at the equator, and when you get to the North Pole, that's 90 degrees. 90 degrees north latitude is usually how it's referred. And similarly, when you go south of the equator, you wind up with increasing values when it comes to the latitude. So eventually when you get to the South Pole, geographic South Pole, that is 90 degrees south latitude. Now, the same thing is used, that same kind of system is used in the sky. Okay, again, when we imagine that all the stars are located on this sphere that surrounds the globe, this imaginary dome in the sky, this is not really how the stars are, but it's a useful model for us. So there's the celestial sphere. And what you do is you project the Earth's equator out onto that celestial sphere. And when you do so, you wind up with what's called the celestial equator. Sometimes it's abbreviated CE. And you assign it a value. You say, okay, it's 0 as well. Well, 0 what? Well, it turns out it's also 0 degrees, and instead of calling it latitude, we call it declination. And so therefore, notice how we have the geographic North Pole. When you extend it outward and let it puncture the celestial sphere, you wind up with the North Celestial Pole, the NCP. Well, in a similar way, just like the geographic North Pole has a latitude of 90, the NCP has a declination of 90. Usually it's referred to as, instead of saying 90 degrees north, usually we just say positive 90, and quite often the positive is just understood. Now in the South Celestial Pole, again, just like the geographic South Pole has a latitude of 90 degrees south, we say it's got a declination of negative 90. Again, and these are in degrees. So therefore, every other, all the other stars, you can put a star anywhere on this, I can put a bunch of dots here. And every star that I put on my celestial sphere will have a unique declination value. The declination value will tell you how far south or how far north that star is with relation or with respect to the celestial equator. So any star that is north of the celestial equator is going to have a positive declination value, with values increasing as you move toward the North Celestial Pole. Any star south of the celestial equator is going to have a negative declination value, with values increasing toward negative 90 as you move toward the South Celestial Pole. Okay, so we've already established what declination is. Again, declination is how far north or south you are of the celestial equator, how far north or south a star is, or any celestial object is north or south of the celestial equator. Okay, that's great. But just like with latitude, it's not good enough to just know latitude. For example, Tupelo, Mississippi is 34 degrees north of the equator. But if you were to tell somebody where Tupelo is, you couldn't just tell them 34 degrees north latitude, because there's a lot of other locations that have the latitude of 34 degrees north. Atlanta and other towns and cities all around the globe are 34 degrees north latitude. So what else do you need? You need another coordinate in order to pinpoint the location of Tupelo. In the case of talking about the Earth, we use longitude. Longitude measures how far east or west you are of the prime meridian. So for example, Tupelo is 88 degrees west of the prime meridian. So if you say 34 degrees north, 88 west, okay, now you have pinpointed Tupelo. In a similar way, with the celestial sphere, you need another coordinate. It's not good enough to just have a declination value. You need another coordinate to pinpoint the location of a star or any other celestial object. And in this case, it is right ascension. Okay, it's essentially longitude for the sky as described. And just like longitude on the Earth, which is just kind of random, where do you start? Because with these lines of right ascension or lines of longitude, these are the ones that all start from the North Pole and go down to the South Pole. And the question is, well, which one is the zero? With the equator, it's pretty easy to know that's the zero latitude or the zero declination line. Which of these lines is going to be your 0 point? Well, it turns out that the ecliptic, that's the path that the sun takes through the sky during the course of the year. Over 1 year, the sun appears to move against the background stars. Not much movement every day, but over the course of weeks, months, you're going to notice that the sun is in a different grouping of stars. That's because it is moving eastward with respect to the background stars. And it makes this circle one time each year. And that path that it traces out is called the ecliptic. And it turns out that the path that the sun makes with respect to the background stars it's a circle, but it's not a circle that is aligned with the celestial equator. Notice there's the celestial equator. And so being two circles, but they're not laying on top of each other, that means they only meet at 2 points. There's only 2 days of the year when the sun is on the celestial equator. And those are your equinoxes, the vernal equinox and the autumnal equinox. And it turns out that for latitude, for right ascension purposes, we choose the right ascension line that goes through the vernal equinox, that intersection of the ecliptic and the equator. That becomes your 0. In fact, it is given as 0 hours. So that's your 0 hour mark. And then the rest of the lines of right ascension are defined as increasing hours east of the vernal equinox. So therefore, so the sun on the vernal equinox, March 23rd, rises on it's on the celestial equator, and it spends all day on the celestial equator. Rises due east, climbs relatively high in the southern sky for mid-northern latitudes, and then it sets due west. Over the course of several weeks or months, it's going to move. It's going to rise every day. It's going to rise a little bit farther north of east, a little farther north of east, until eventually, when it gets to this point in its orbital path, it is as far north of the celestial equator as it's going to be all year. That is the summer solstice, around June 21st. Summer solstice. Then, as it continues around here, every day after the summer solstice, every day after June, it's going to get a little farther. It's going to move a little bit farther and farther back toward the east point when it rises, or toward the celestial equator, until eventually, by September 23rd, I should probably put these dates here. September 23rd, that's when it is on the celestial equator again. We call that another equinox. So this one's in March. And then after September, in the late fall, it's going to be getting farther and farther south of the celestial equator each day until eventually it gets to a point where it's as far south of the celestial equator as it's going to be all year, and that is your winter solstice. The sun rises way south of east, climbs low in the southern sky for mid-latitude northern hemisphere viewers, and sets well south of west. That's your winter solstice. And then every day after the winter solstice, remember, winter solstice is around December 21st. Every day thereafter, it's going to move a little bit closer to the celestial equator until eventually by March, it's back on the celestial equator. Now, we said that the vernal equinox, that intersection point between the ecliptic and the equator, we call that 0 hours right ascension. And it's a full circle which goes up 24 hours. So therefore, the summer solstice, because it's 1/4 of the way around this circle, we call that right ascension 6 hours. And for the autumnal equinox, we call that right ascension 12 hours. And for the winter solstice, we call it right ascension 18 hours. And by the time you get back around to the spring equinox, you're back to essentially 0 hours. You go up to 24 hours. We reset it and call it 0 hours. So now by knowing these different lines of right ascension, now when you put a bunch of stars on here, you can identify the location of a star or any celestial object on the celestial sphere by giving the two values. Its declination, how far north or south it is of the equator, and its right ascension, how far east it is of the vernal equinox. So for example, the sun on the vernal equinox has a declination of 0 degrees, and it's got a right ascension of 0 hours because it's smack dab right on the vernal equinox. When it is at the summer solstice, when it's at this point, we would say it's got a declination of about 23.5 degrees is how far north it is of the celestial equator on the summer solstice, and it's got a right ascension of 6 hours. When it's back here at the autumnal equinox, it's got a declination of 0 because it's right on the celestial equator again, and it's got a right ascension of 12 hours. It is 12 hours around eastward from the vernal equinox. And then finally at the winter solstice, it's got a declination of around negative 23.5. Remember, it's south of the celestial equator at that point, so we give it a negative value, negative 23.5 declination, and it's got a right ascension of 18 hours.
Okay, so let's get some practice with this whole declination and right ascension thing. Declination, as we've already talked about, is pretty easy. Notice we have we got a globe here. We've got our celestial sphere. In fact, we can put in some labels. There's my North Pole, my South Pole, geographic. Same thing with my equator. Remember, as we project these onto the celestial sphere, we get what's called the celestial equator, which remember that's declination 0. And we have, of course, the north and south celestial poles. Remember, those declinations are positive 90 and negative 90 respectively. And that makes sense. That's pretty common. That's, notice it sounds very similar to the latitude values we have on Earth. 0 degrees for the equator, 90 degrees north for the North Pole, 90 degrees south for the South Pole. And therefore, if I wanted to choose a star, such as this one, I would say, well, gosh, what are its coordinates? The declination is pretty easy to spot. Notice that it is above, it's north of my celestial equator. Well, how far? About 60 degrees. Remember, the 90 degrees north would be the north celestial pole. So this is about 60 degrees, but that's not good enough because any star that's on this gray band here would have a declination of positive 60. So to pinpoint that star, I need another value. I need the right ascension. How do I get it? Remember, the right ascension is built off the ecliptic. So when I throw the ecliptic on here, remember the ecliptic is the apparent path the sun takes through the sky over the course of an entire year. And when I throw the ecliptic on there, I notice that it intersects the celestial equator in two spots, the vernal equinox and the autumnal equinox. And remember, these are in hours. So the 0 hour is my vernal equinox. Halfway around the sky, when I go back to the autumnal equinox, that would be 12 hours way back here, autumnal equinox. So the question is, well, gosh, what's the right ascension of this particular star I'm interested in? Well, notice that it is east of my vernal equinox, and the right ascension values always increase in hours east of the vernal equinox. And it's about 1/3 of the way to my autumnal equinox. So here's 12 hours, so that would make this about 4 hours. And again, I could slide this around. What if I go up here? Notice the right ascension here would be 6 hours. If I find a star that is on the same right ascension line as my autumnal equinox, notice that it's got a declination of positive 47 and a right ascension of 12 hours. Notice if I had a star right on the celestial equator at the autumnal equinox, it's going to have a declination of 0, and it's going to have a right ascension of 12 hours. Now if I'm over here, notice my ecliptic is now below my celestial equator. So, but my values of right ascension continue to climb. Now I'm at 18.7 hours. Remember, here's the winter solstice. The sun would be south of the celestial equator. It's going to have a negative declination. Its right ascension is going to be 18 hours at the winter solstice. And eventually it's going to increase until I get back to my vernal equinox, 24 hours where we start all over again. Okay, so this simulation actually ties into the diagram from the previous slide, as well as this is the same diagram on page 24 of your textbook, but I wanted to talk about the zodiacal constellations. Again, these just happen to be the stars that fall in line with the path that the sun takes through the sky each year. So there's nothing special about these constellations apart from the fact that we tend to notice them because these are the stars that tend to be close to the path that the sun, as well as the planets take during the course of the year. So they tend to, get a little more eye time. We pay attention to these a little bit more. So let's go ahead and start things in like early January and help you understand what this thing is showing. So in early January, the sun would be in Sagittarius. Now that would mean that you wouldn't actually see Sagittarius in January because, well, why is that? Because only the people on the daytime side of the Earth are seeing Sagittarius in early January. And of course, Sagittarius is in the sky, but these are little pinpricks of light, little stars that are trying to compete with the sun. And therefore, you wouldn't see Sagittarius, you wouldn't see Scorpius, you wouldn't see Capricornus in early January because they're in your daytime sky. What would you see? Well, eventually, as the Earth would rotate during the course of a day, you'd spin around to the nighttime side, and you'd see things like Cancer and Gemini and Taurus in early January. And again, these are all background stars. They're so far away that they don't change their positions at all. They are essentially fixed on the celestial sphere. The sun, however, is not. Why is that? Because it's much closer. It's a star, just like all these are all stars. But the sun is so much closer to the Earth than these stars are. The sun is only 8.3 light minutes away. All these other stars are light years, sometimes hundreds or thousands of light years away. So the sun is much closer, and therefore as the Earth orbits the sun appears to move with respect to these background stars. So you can see during the course of one day, if I just move one day, notice the Earth is spinning. The sun does move. It doesn't move appreciably. It's still in Sagittarius. But notice that over the course of several weeks or a month, when I get into February, early February, notice now that the sun is no longer in Sagittarius. It is now located in Capricornus. And so forth and so on. Notice that, again, the sun is moving eastward with respect to the background stars. Why is that? Because the Earth is orbiting the sun counterclockwise when viewed from above. And so by April, notice that now, oh, gosh, my sun is in Pisces. And notice that my daytime constellations have changed, as have my nighttime constellations. Now I'm seeing an entirely different collection of nighttime constellations. When I spin around and get to the nighttime side of the Earth, I'm seeing Libra, I'm seeing Virgo, I'm seeing Leo. So this little simulation helps to explain why the nighttime constellations change depending upon the time of the year, and it also explains about your birth sign. And it turns out that a lot of us think that we were born a certain sign, and most likely you're actually a different sign. More on that later. But if you don't quite understand all this, I encourage you strongly to check out my YouTube video about the signs of the zodiac. It's located in the Module 2 lab activity. Notice there's 2 lab activities in this module. It's the second lab activity. If you scroll all the way down to the bottom, you look at several of the tutorial videos. I think it's the last one. It's about the signs of the zodiac. You'll see me acting crazy and spinning around my classroom and trying to explain these signs of the zodiac, and I hope you enjoy it. Okay, now that you're all experts at right, ascension, and declination, here's a way of explaining the seasons. And the reason that the seasons are different is because of the position of the sun with respect to the celestial equator during the course of the year. The sun, as we mentioned, does not maintain its same position in the celestial sphere the entire year. It moves. And in fact, as we already talked about, on the vernal equinox, the sun is right on the celestial equator. And then it moves eastward with respect to the background stars during the course of weeks, months, etc. And so its right ascension changes, right? So as well as its declination, because at the vernal equinox, notice that it is on the celestial equator, which means it's got a declination of 0. Notice here, the diagram here is a little different. Here's my celestial equator. So all these values up here, anything that's located north of the celestial equator has positive declination. Anything south of the celestial equator has negative declination. So we know that on the vernal equinox, the sun is right on the celestial equator. It's got a declination of 0. We also know that it's got a right ascension value of 0 hours. That's just by definition. The vernal equinox is 0 hours right ascension. Now, as time moves on, notice that over the course of several weeks, months, eventually, in late June, remember the vernal equinox is in late March, by late June, now the sun is no longer on the celestial equator. It's actually as far north of the celestial equator as it's going to be the entire year. It's got a positive declination value. And in fact, it's a positive 23.5 degrees declination. And remember, it is now east, it has traveled eastward of the vernal equinox, and therefore its right ascension value is 6 hours. And so forth and so on. It'll continue on its way around until by autumn, it's way over here. It's back on the celestial equator. So it's again got a declination of 0, and it's got a right ascension of 12 hours. And so forth and so on. So we can essentially boil all that down into a 2D representation, which is the graph that you're going to see on the next slide. Okay, so sometimes it's useful to actually make the celestial sphere, just put it on essentially a 2D representation. So here I've got a chart that shows declination values as well as right ascension values. Again, those are how we map out the celestial sphere. But here we're just going to be focusing on the position of the sun. Because remember that the stars on the celestial sphere, they don't change their positions. That's the beauty of the celestial sphere and the right ascension and declination system, is that the background stars don't change. So if I were to map out their positions over the course of the year, I just have the fixed values. But for the sun, it does change. And therefore, its declination value and its right ascension value is going to be different every day. And that's because, again, the Earth is orbiting around the sun. So here we are in early January, and notice that the sun's declination is negative. In fact, it's pretty close to negative 23.5. It's a little shy of that. Its right ascension value is, well, it's a little bit past 18 hours. It's, gosh, 19 hours or whatever. Notice what happens when I animate this thing. Isn't that interesting? So here we are in early March. Notice that my declination has become less negative. It's actually getting closer to 0. And my right ascension value has climbed. It's almost to 24. By the time, whoops, I'm just going to go ahead and just let it animate and let you see the whole progression. So now, boom, vernal equinox. My declination there was 0 for a moment, and my right ascension was 0. Now, summer solstice, right ascension 6 hours, declination was positive 23.5. Now we're approaching the autumnal equinox, 0 declination, 12 hours right ascension. Here we are at the winter solstice, and we're going to have 18 hours right ascension and negative 23.5 declination. And then finally we return back to the vernal equinox. So you can see that the sun changes its position. Half of the year, it's above the celestial equator. It's essentially in the northern sky. Half of the year, it's in the southern sky. And 2 times a year, it intersects the celestial equator at what we call the equinox. Once you understand that the sun does not have its same position during the course of the year, that it changes declination, it changes right ascension, the important part is really to understand that the declination changes. And because the declination changes, the latitudes that receive the most direct radiation change during the course of the year. So that's what this little animation is going to show, is that as you take it on through the year, as we get into the late May and into June, notice that it's the Tropic of Cancer that's receiving the most direct radiation on the summer solstice. When the sun is on the celestial equator, that means that the equator gets the greatest amount of sunshine on the equinox. And then as we get into the winter time, when you get to the winter solstice, it's the Tropic of Capricorn that's receiving the most direct light. And hopefully you've taken the time, you've perhaps built one of those solar motion demonstrators, or at least watched my demonstration of the solar motion demonstrator in the lab, the Module 2 lab activity, Motions of the Sun. I've got a video where I build a solar motion demonstrator, and hopefully By doing that, or building one, or at least viewing the video, you've gained an appreciation as to why it's hot in the summertime in the northern hemisphere and why it's cold in northern hemisphere winter. It's not because of proximity to the sun. It's not the proximity effect. There are two other very important reasons for why it's hot, and hopefully the angle of the sun and the fact that that changes during the course of the year clues you into those two very important reasons. You may have noticed in one of the lab activities that, or in one of the videos below the lab activity, that I have students in my traditional classes build a solar motion demonstrator, and hopefully, you even got a chance to try it. And the question is, well, why do I do that? Well, it's to disabuse people of the thought or the idea that the sun rises in the east and sets in the west. If you stop somebody on the street and say, "Where'd the sun rise this morning?" They'll say, "Well, in the east." And you tell them ask them where the sun's going to set in this afternoon or this evening, and they'll say, "In the west." It turns out, if you're really, really picky, and by east mean due east and west mean due west, those people are not always correct. In fact, they're much more likely to be incorrect than they are correct. And here's why. This little demonstration, this simulation here, will allow us to see the actual location of the sunrise at different times of the year. So I'm going to hit play. And notice that the sun does not rise in the same spot every day of the year. It moves quite significantly. And the ancients actually noticed this. They noticed that the sun, they would wake up and they'd see, gosh, the sun changed its position with respect to some trees or a mountain or something like that on their eastern horizon, and started to notice the pattern that the sun tends to, well, it rises south of east during the fall, winter, early spring. It rises north of east in late spring, summer, and early fall. And it reaches points where it actually turns around. So notice that it tends to change its position, but right around June, in kind of late June, notice that for several mornings in a row, it rises in the same position. Wouldn't it be nice if we had a name for that? It turns out there is a name for that, solstice. Solstice comes from the Latin sol, sun, and stis, stop. The sun appears to stop for several days, or it appears to rise at the same location several days in a row, right around these special times of the year, late June, and it turns out late December. Oop. Notice that the sun, again, appears to stop, solstice. Very interesting. Now, notice that when does the sun rise in the east? All right, I missed it by a couple of days there, right around March 21st. It rises due east. Well, and it turns out that it rises due east because it's on the celestial equator on that day. And so it rises due east, it climbs high in the sky, depending on how high depends upon your latitude, but then it sets due west. And that's true not only of your location, but any location on the Earth. The sun on that day rises due east, sets due west. And it turns out that it is in the sky for about 12 hours. It's in the sky for about 12, in the daytime sky for about 12 hours. That means it's below your horizon for about 12 hours. So your night is equal to your day on this special day. Well, gosh, wouldn't it be nice if we had a name for that? We do. It's called equinox. The night is equal to the day. Nox means night in Latin. So the daylight hours are about the same as the nighttime hours. And the cool thing about this simulation is you can actually change, you can look west as well. And it turns out that the same thing is at play. During the summertime, the sun rises north of east, climbs high in the sky, sets north of west. In the wintertime, well, let me go back to, I missed my fall equinox. My fall equinox, which is in late September, sun rises due east, sets due west. And then as we get into the fall months and into the winter, right around, there's Christmas, right around December 21st, the sun rises well south of east, climbs low in the sky, and sets south of west. And that is your winter solstice. So hopefully that gives you some insight as to the location of the sun's rise and set during different times of the year. Okay, so in the last slide we talked about why the sun rises at different locations during the course of the year, and this has everything to do with
why you have different lengths of days during the year. Now, you may have remembered, I'm going to go ahead and actually use the simulation. I'm going to take it to Tupelo, about 34 north. And let's go ahead and take it to, let's go to the, keep it simple. Let's take it to the fall, I'm sorry, to the spring equinox. If you recall, on the spring equinox, March 21st, we said that the sun rose due east, set due west, and was in the daytime sky for about 12 hours. And that's what this graph is showing us. It's showing us that, yes, on that date, we have 12 hours of daylight. Notice that as you get in through the late spring and into the summer, early summer, your days are now getting longer, right? You're getting more daytime hours than you are nighttime hours. In fact, at the summer solstice, June 21st, that's when you have the longest day of the year. You have 14.3 hours of daylight in Tupelo, Mississippi on that day. And as we continue on into the fall, notice that September 21st, thereabouts, you have the fall equinox. Again, equinox, same length day, same length night. Then you get to the winter solstice, December 21st, and now you've got the shortest day of the year, 9.7 daylight hours. And so that's the way this graph is read, and that's the cycle. Now notice that you do have more dramatic, as you change your latitude, the curve becomes more dramatic. But two important things to understand is that no matter where you're located, now this is up at 61.5, this is somewhere up in Alaska. On the fall equinox, I'm sorry, on the spring equinox, March 21st, notice even in Alaska, you still have 12 hours of daylight, 12 hours of nighttime. So the equinoxes, you still have 12-hour days. But of course, notice that the number of daylight hours on the summer solstice becomes much more dramatic, a lot larger. Right? It's almost always day. In fact, if we take it up above the Arctic Circle, let's go up above 66 degrees north. Let's go up to like 70 degrees north. Notice that now there are certain times of the year when the sun does not set. So all through, if you're at 70 degrees north, from late May, May 21st or so, all the way through late July, the sun never sets. You have 24 hours of daylight during those time periods, but you pay a price because as you get into the winter months, notice from late November through late January, now no daylight, total night all the time. So the fact that we have different lengths of days depends entirely upon the tilt of the Earth, and hopefully you've picked up on that. Okay, so we've just talked about the fact that the sun rises in different locations during different times of the year, and of course that affects the amount of daylight hours that you have. Also want to talk about how intense the sunlight is that you receive depending upon the time of the year. And so I want to show you this cool simulator demonstrator that shows, this is from Lincoln, Nebraska, and it shows just a picture. And in fact, the picture is looking eastward. I'm going to just lay on the, so we're looking in the background, we are seeing east. And of course, in the foreground, that's kind of toward the west. As we look to the right, that's looking south, and looking to the left, that's looking north. I'm going to take off the directions. Now that you're oriented, I'm going to take the directions off just to make this a little easier to see. Another thing I want you to notice is that we are looking at the noontime shadow of this building here. And we can see that from our little diagram over here. We're seeing the position of the sun in this photo. So it is in our southern sky, as it has to be, and it's highest in the sky. You'll notice there's a line here. That's one thing I'm not sure if I've explained to you in the notes here. That's what's called the meridian. The meridian divides the sky essentially into an eastern half and a western half. And so we are looking at the sun when it is on the meridian. Well, that just happens to be noontime. Local noon is when the sun is crossing your meridian. In the morning, the sun is east of the meridian. In the afternoon, it is west of the meridian. Wouldn't it be nice if we had terminology that would help us remember that? Well, we sure do. Do you ever hear the terms AM and PM? AM stands for ante meridian, before meridian. It's the sun. The sun is in the sky, but it has not yet reached the meridian yet. PM stands for post-meridian, after meridian. The sun is now in the part of the sky that is after the meridian. So we're going to be looking at the noontime photo of this plaza during the entire year. And I'm just going to let it play. Hopefully it doesn't look too glitchy. But notice
the sun's position changes during the course of the year. Its noontime position changes during the course of the year. Sometimes it's much lower in the sky. Sometimes it's much higher in the sky at noon. And of course, the height of the sun, the angle of the sun, will affect the length of the shadow cast by the building, or cast by our little guy there. So notice that when the sun is lowest in the sky, which is in the wintertime, the shadow is the longest. When the sun is high in the sky, highest in the sky, which is June 21st, summer solstice, the shadow is the shortest. Ain't that something? Okay, so now we're going to talk about Earth's climate. And the very fundamental question that I want to ask is, why is it hot in the summertime and why is it cold in the wintertime? Let's talk about northern hemisphere. Why is it hot in the summer? Why is it cold in the winter? If you said that it's because the Earth is closer in the summertime to the sun and farther away from the sun in the wintertime, I'm going to reach through this computer screen and grab you and shake you, because that is not true. That is what everyone, no, not everyone, a good number of people instinctively say that. I call it the campfire effect, or the proximity effect. People think, well, gosh, if there's a campfire, when I'm close to it, I'm warm. When I'm far away from it, I'm cold. But in the Earth's case, the Earth is never really close or far. Technically, it is. The Earth goes through a essentially circular orbit around the sun each year, and you should know that. But it's not a perfect circle, just like my drawn circle is not perfect. There are times when we are closer to the sun a little bit, and times when we are farther away. The average, as we've already discussed, is about 100 million miles. It's 93 million miles is how far, on average, the Earth is from the sun. But at times it's closer, 91.5 million miles. At times it's farther, 94.5 million miles. But what's a couple of million miles between friends? It's still essentially a perfect circle. So we're never really that much closer or farther away. That is not what drives the warmness in the summertime and the coldness in the wintertime. It's all about the fact that the Earth is tilted with respect to its orbital plane. And therefore, sometimes the sun is hitting the northern hemisphere with more direct radiation and for longer time, longer daylight hours. And sometimes during the course of the year, the sun is hitting the northern hemisphere with lower quality, more glancing radiation, and for shorter numbers of hours during the day. That is what drives the seasons. It's not the proximity of the Earth to the sun. Now, over longer time scales, there are some astronomical drivers to climate. Have we had ice ages and stuff? Yes, we have. Is there an astronomical tie? Well, that's what a scientist named Milankovitch proposed. He thought that maybe there were some connections. And so he did some research. And he realized that, yes, the Earth changes its eccentricity. That means the roundness, the circularity of its orbit does change over time. Sometimes it's a little more round, sometimes it's a little less round. But the period there is about every 100,000 years it goes through its eccentricity changes. Precession, that's the amount of wobble, because the Earth does wobble. As we know, the Earth's geographic North Pole is right now pointed toward Polaris. That has not always been the case, nor will it be the case. It will change its North Celestial Pole over time. It wobbles once on its axis every 26,000 years, and that will affect then how the Earth is tilted at different times of the year with respect to the distance from the sun. And then, of course, there's the inclination of the Earth's axis. How tilted are we? Right now we're at about 23.5 degrees, but that changes from about 22 to about 24 degrees over time. And what Milankovitch thought is that when you factor in all these astronomical drivers, they could give us an idea as to why there have been ice ages in the past, why the Earth has gone through periods of warm periods and cold periods. And that's the Milankovitch hypothesis. Okay, as we just mentioned, the Earth is tilted with respect to the plane around which it orbits the sun. That's what's called the plane of the ecliptic. And so yes, you notice that right now the Earth is tilted about 23.5 degrees with respect to that plane. In fact, the way this simulation is shown, this is northern hemisphere summer, because notice that the northern hemisphere is tilted toward the sun and the southern hemisphere is tilted away from the sun. And notice that there's a section, there's an area on the Earth. Remember, just imagine that the Earth is spinning eastward. There's a part of the Earth close to the geographic North Pole that would be, even with the sun spinning, is going to be in sunlight the entire day. So that's essentially above the Arctic Circle. You're going to have areas that are seeing 24 hours of daylight. Notice down in the southern hemisphere, from a similar argument, you're going to have parts of the southern hemisphere that are essentially south of the Antarctic Circle that are in 24 hours of darkness. And that's because of the Earth's present obliquity, or the angle at which it is tilted to the orbital plane. Now imagine that we had zero obliquity. What if the Earth was spinning perpendicular to its orbital plane? Notice that there you would have all parts of the Earth getting some daylight and some nighttime all the time. So think about how a change to the obliquity of the Earth would affect your seasons, the length of your seasons, the severity of your seasons. All right, pretty cool.